Okay, now is our last topic. We're going to introduce you the LEN model. Okay, so our objective is to have a model that studies the uncertainty of random outcome. But in the previous video, when we introduced the first model, that's the binary model. Your outcome may just be either 0 or 1. So here we want to somehow broaden our understanding and to study a random outcome that is continuous. Okay, so that's our objective. But unfortunately, researchers have shown that if we consider a moral hazard problem with a general random outcome, then the problem can be easily intractable. We are unable to find any analytical solution, and then the study cannot proceed. So that means we need to somehow narrow down and consider some special types of distributions. So that's the LEN model, a tractable model with continuous outcome. In the LEN model, there are three components. First, the random outcome will be assumed to be following a normal distribution. And then, the utility function must also have a special format. In general, it's concave, but here we need to set it to be negative exponential. And finally, the compensation plane cannot be too weird. The compensation plane must be linear. So technically, the outcome Q will be assumed to be A plus epsilon. A is the action or the effort level, and the epsilon is a normal random noise whose mean is 0 and the variance is sigma square. Okay, this is a normal distribution, and that means your expected value of Q will just be A, and there is some random noise. The agent's utility function will be set to be following this particular format. Okay, if you think about the functional form, first you have an exponential function, and then the exponent is multiplied by -1, and then we make the whole function multiplied by -1. So what does that mean? Suppose you have an exponential function like this. Then once you multiply the exponent by -1, you're going to get something like this. And finally, if you multiply the curve by -1, then you're going to get something like this. Okay, and then this is your u of z. So the x-axis is z, and the y-axis is u. So you're probably wondering why the utility is negative, but that doesn't really matter. All you need to do is to, for example, add 1 to the function. Okay, then your utility can get to positive, and that doesn't matter at all. So we will adapt this functional form, and you will be aware that something you can do is to add some constants to it so that you can scale it up or down. Here we have a coefficient called eta. Eta determines the shape of the function. Okay, so we say eta is the coefficient of absolute risk aversion. One thing we will say is that if eta is becoming larger, then the agent becomes more risk averse. Or if eta becomes 0, then actually this reduces back to a linear function. Then when eta is 0, that means this customer is risk neutral. Finally, the compensation plane is somewhat restricted. It must be in a form like T plus SQ, where T is the fixed payment and the S is the commission rate. So that means I cannot design a nonlinear compensation plan, or a compensation plan that if outcome is this, that's good. If outcome is that, I shoot you. No, I cannot do that anymore. The compensation plan now must be linear. Okay, so now we have the model. our task is to derive the optimal compensation plan and the equilibrium action. So let's try to do this. First, we need to analyze how the agent will choose his action. So, given an offer, TS, the agent will choose action A to maximize his expected utility, which is this guy. Okay, Z is the random payment, depends on T plus SQ, that's the first part, and also 1 over 2 A squared. 1 over 2 A squared, I forgot to put it in the previous slide. This is the cost of exerting efforts. Okay, so that means I, as an agent, if I put some effort, I can change my the distribution of my random payment. But in any way, I need to pay a cost. If we further derive the formula, then we can say this Q is random, right? And Q is A plus epsilon. Because in all the things here, only epsilon is random, so we may simplify the expected utility to this one. So what we did is to decompose this exponential function to two pieces. This part is a constant, and only this part contains a random term, epsilon. And after we do that, we can take the constant outside the expectation. So we get this. Okay, this is just a constant, and our task would be to find what's this expected value. Okay, but the good thing of this model is that the expectation is actually a bilateral Laplace transform of this normal random variable epsilon. Okay, or you don't really need to know what's this, but to get this expectation, there is a way. So in general, given any normal random variable and a constant, if we want to calculate this, then we would get this guy. Okay, so this expectation can be done. So this is a typo, this should be plus. Okay, this should be plus. Okay, so let's see how to do this magic. So I have my task. My task is to find the expected value of e to the power of r epsilon, where r is a constant and epsilon is a normal random variable. So I follow the formula of expectation. I have this function e of rx, and I need to do a weighted average of this guy with respect to the weights as the PDF of the normal random variable. Okay, this is the PDF of a normal random variable. Once we do that, we take this constant outside and combine these two exponential terms into this guy. And then we do some manipulations. For the numerator, we add r squared sigma to the power of 4 and minus r squared sigma to the power of 4. Once we do that, we can have a square for the first part and have the other term at the second part. And now we decompose the two parts again. The first part here goes to here, and the second part here is a separate term. Okay, then all we need to do is to take this outside, because this term has nothing to do with x. X is only here. And once we take this outside, we also take that 1 over square root of 2 pi sigma into the integral. And if we check this whole thing would just be the PDF of another normal distribution whose variance is still sigma squared and whose mean is r sigma squared. Okay, the mean is here. So if you check the PDF of normal random variable, you can verify, oh, this is true, oh, that is true. So that's good. And the best thing is that once this is a PDF of a normal random variable, then the whole term here would just be 1 because that's probability theory. Okay, then all you have is the remaining thing here. That's the end of the proof. So once we have this, the agent's expected utility can be further simplified. We have the one constant term outside the expectation, and the expectation gets to this if we replace r by negative eta s. Okay, so then we combine the two terms and get this one. Okay, not a surprising thing because we know how to do that. Finally, we define something called the certainty equivalent of the agent's utility function as the exponent. Okay, so we have the exponent. We define the exponent as a certainty equivalent as a function of the action. Okay, what's this? This is something that people use to measure, to combine the expected return and risk of a random outcome. We have two terms. First is this guy. What's this? This is exactly the expected return by exerting effort A. Okay, by exerting effort A, we get this random return. But interesting is that this one, on the second term here, measures the risk due to the uncertainty. I, as an agent, I don't like risk, so I have eta. When eta becomes higher, I do not like risk anymore. I also have risk coming from two things. First is the commission rate. If I have a commission rate, then that means my payment is given by the outcome. Okay, the sales outcome will determine my payment, which is risky. Or if the random variable itself is more dispersed, then there is more risk. So I can combine the three risks and get a measurement in this way, okay, in this closed form. So certainty equivalent really combines the expected return and the risk, okay, and that means this is a fair representation of the agent's utility function. Okay, if we have this, that's great. Why? Because the agent's expected utility is this. The agent should try to find A to maximize this function, which just means to maximize the certainty equivalent, because the exponential function is monotone and increasing. So once we know this, then all we need to do is to find A to solve this. Obviously, the answer would just be small s. And what does that mean? This is very intuitive, because that means if the principal increase the commission rate s, that's going to increase the effort level of the agent. A higher commission rate can induce the effort level. Okay, and in one extreme case, if s is 0, then the agent will not do anything. If s is 0, then a would just be 0. Okay, so now it's time to study the principal's contract design problem. The principal's expected profit is this one. The random profit is 1 minus s times q minus t. Q is the random outcome. 1 minus s is the share to the principal. T is the fixed payment. Okay? In equilibrium, we will have q equals a plus epsilon, which is just s plus epsilon. Because in equilibrium, the equilibrium effort level would just be s. That's why we get this. Okay? We decompose q into s and epsilon. And the expected of epsilon is just 0. Then we get this as the principal's expected profit. The trade-off is very clear. If I increase the commission rate, then the effort would become higher, but the share that can be retained by the principal would be smaller. The agent certainty equivalent in equilibrium will be CE of S, because again, the action would just be S. So if we plug in S into A, We get this, which is in this format. Finally, the principal's problem can be formulated as choose T and S to maximize its own expected profit, subject to that the agent's certainty equivalent must be non-negative. So here, we consider the certainty equivalent instead of the utility function. But you know it doesn't really matter because you can always scale each other. If this thing is non-negative, that means the negative exponential utility function is above a certain level. If you actually need the utility to be above, for example, 0, then this would become another constant. But as long as the right hand side is a constant, it doesn't really matter. Okay, so obviously the constraint must be binding at any optimal solution. So the principal's problem can be reduced to this one. Well, you can see there is a typo. There should not be this term S, a T. Okay, so now we want to choose S to solve this obviously concave function. The first order condition gives us the optimal commission rate in this format. Okay, so that's the analytical solution of this principal agent problem. Now it's time to give some economic interpretations to this final outcome, the optimal or the equilibrium commission rate. So first, we can see this is positive, good. And second, this is less than 1, also good, because it doesn't really make sense if the commission rate is above 1. And then S is determined by eta and the sigma square. S actually decreases in eta. That means when the agent becomes more risk averse with a higher eta, then the agent would prefer a lower commission rate. Okay? Because if I am really risk averse, then I would highly prefer a fixed payment. Then the principal will cut down my commission rate. And you may expect the final system would become less efficient, because this guy don't want risk, so this guy don't want a high commission rate, then this guy will not work. And that's also reasonable, because if you exert efforts, your outcome, your benefit is random, but in any case, your cost is deterministic. So if you are really risk averse, you would not do this. You actually will not do a salesperson, you probably will do another job. At the same time, S star decreases in sigma square. Okay, decreasing in sigma square. That means when the outcome becomes more unpredictable, when the random noise becomes even more noisy, then the agent would also prefer a lower commission rate. Because I am risk averse, then if the outcome is more unpredictable, I would really hate commission rate because that gives me a lot of risk. Then I would again prefer a higher fixed payment. Okay, so that's something showing that this commission rate or this compensation plan makes sense. Okay, and very quickly you can see if the agent is risk neutral, eta would become 0. Okay, eta would become 0. And if that happens, S would become 1. Or if sigma square is 0, then also S would become 1. What does that mean? That means the problem goes back to the first best. That means the problem is not a problem. If the agent is risk neutral, then random noise doesn't mean anything because the agent just don't care about risk. If there is no randomness, then risk aversion is not a problem because the payment would just be deterministic. Okay, so that directly confirms our intuition that risk aversion and randomness are required if we want the moral hazard problem to show up. There's one final note. We are dealing with a linear contract. That's why we get this compensation plan. But in general, no one says your contract must be linear. Okay, so no one says this optimal commission rate is really optimal to the principal, because if the principal want, the principal can actually design a much more complicated contract to see if that is possible to make his profit even higher. Okay, that's possible, but that's beyond the scope of this course and beyond most of the scope of the analysis, because it's in general intractable. Okay, so that's why LEM model is still useful even though it is suboptimal, but it's tractable and linear contract is widely accepted in practice. Okay, now it's time to give a quick summary. Hidden actions creates the moral hazard problem. Okay, because the action is hidden and costly, the agent must be incentivized or compensated for his action. Compensation may or may not be inefficient. Okay, so I delegate a job to the sales agent or to the agent. I need to compensate him. Sometimes the compensation can be designed so that I can recover the first best outcome. Sometimes I cannot. And the factors that determining whether the outcome can be efficient are here. Okay? Delegation is really a problem when all the following elements exist. The action is unobservable, the outcome is uncertain, and the agent is risk averse. If we have all of them, then we have moral hazard. Otherwise, delegation does not really create a problem. Okay, so that's for adverse moral hazard. Now this is the end of this whole series of lectures. So overall, we have studied screening, signaling, and moral hazard, right? Screening and signaling is under the categorization of adverse selection, and the moral hazard deals with hidden action is another thing. But altogether, they form the theory of information asymmetry. The whole thing of this series of lectures is that the world is decentralized, right? And the decentralization may bring in the incentive issue because you cannot control that guy, so you need to provide incentive for that guy to do something. And we have all kinds of ways to deal with the incentive problems, basically mechanism design or contract design. And information asymmetry would aggravate the issue, would make your contract design problem harder, okay, because there is something you don't know. Then you really need to design a more complicated contracts, and that's the whole thing of this series of lectures. Okay, I hope you enjoyed. Thank you.